Hello, this is David Johnston with another thrilling episode of Entropy Extractors and random numbers and things like that. This is the fifth part of the Entropy Extractors and the last part. And we're going to look here at SP800-90B Entropy Extractors, which is a NIST government specification in the USA about entropy sources. So we've looked at various different things to do with extractors, how they're defined, simple ones, multiple input extractors, single input extractors, and so on. And here, this last one, we're looking at the standardized entropy extractors that NIST have specified in a document called SP800-90B. So the different SP800-90 documents, first being SP800-90A. This describes what in the spec is called deterministic random bit generators. Here they're called, normally they're called PRNGs, pseudo-random number generators, which isn't a good name as we've discussed before. Deterministic random bit generator is a fairly accurate name that they use in that spec because the algorithms are deterministic and they generate bits that are random. The one we're looking at here is SP800-90B. Now, this is a spec where you could say it's a spec that's doing too much because it covers lots of different things: noise sources, entropy extractors, online health tests, offline health tests, entropy estimation algorithms, and things like that. And so it's quite a complicated spec. And in that document, they call the thing we call entropy extractors normally a conditioning component, or in the case of the algorithms defined within it, a vetted conditioning component, because they've decided that those are the ones that they're willing to certify. And then the last of the specs is SP800-90C, which is how do you construct a random number generator from the other parts in A and B. So it's really how you plug A and B together. And that is still a draft. There was an updated draft released recently, which hasn't been on public release. It was shared to a few people, including myself, outside of NIST, and to do initial review, but I'm sure the public draft will be out very soon. So here's how the standard 90B starts. There's the URL to where you can get the PDF. And when you look through the document, one of the early things you come up to is this diagram here. And what 90B covers is everything within the gray box. And so you've got some kind of analog noise source, which is a physical thing rather than just an algorithm. And it's picking up noise from the environment and turning it into bits. And so we have the digitization stage, which is there to turn it into bits. And then that data comes out, and so with the analog noise source and the digitization, it gets to be called a digital noise source because it's this black box that outputs digital bits. Then we have the raw data, so there's been no post-processing, and that goes via this dotted line into the health tests, which is an online running continuously test, which is looking at the output from the noise source and deciding whether or not it's broken. And then if it thinks it is broken, there'll be some sort of error signaling coming out. And then the data also goes to the conditioning component. Now it says here it's optional, and it isn't really optional because the ways in which it could be optional are, first, that you have a perfect analog noise source that's producing perfectly random data, but that thing cannot exist in this universe. So that's not really practical. And then you have, in SP800-90A, we'll look at these things called derivation functions, which you might use instead, although I would recommend against it, and we'll get to why. And so that comes to the output of this whole thing. And the next thing down the line would be the DRBG, deterministic random bit generator, which is specified in SP800-90A. So we have this entropy source model and we're going to be looking at the conditioning component. So that's this guy here. So if you look in the spec, you'll find section 31511. They tell you what are the approved conditioning components, or the vetted conditioning components. And the first is HMAC, so hash message authentication code. The spec there is FIPS 198, with any approved hash function in FIPS 180 or FIPS 202. So things like SHA-256 or SHA-3. Those algorithms you can use as an inner algorithm in HMAC, and that creates a message authentication code, which also works as a entropy extractor or conditioning component. CMAC is another message authentication code based on a block cipher. So its spec is SP800-90B, and they want you to use AES. And then CBCMAC is very similar to CMAC, but it's a bit simpler and came a lot earlier. And as a message authentication code, CBCMAC has problems, and it's not approved for use as a message authentication code by NIST as a result. It has cryptographic problems. It's somewhat easy to perform certain attacks. For instance, in TLS, there were attacks against CBCMAC used there. But when you use it as an entropy extractor, as we'll see a bit later, CBCMAC is perfectly fine. And in Intel, we used CBCMAC for our entropy extractor long before 90B existed. And then they put out the first draft of 90B, and they didn't include CBCMAC. So we wrote off letters to NIST saying, put CBCMAC in. And we put it in there because there was a proof by Evgeny Dodis that it is a good entropy extractor. So we presented that information, and they put it in the spec. So then it became part of the spec, and later the spec was approved. So CBCMAC is in there. And they also added CMAC at the same time. Then they have these unkeyed functions, and this is where we have the any hash function. So again, FIPS 180 or FIPS 202, HMAC, SHA-256, SHA-3, that kind of algorithm. And then these two other ones with DF, which stands for derivation function. So the hash derivation function and the block cipher derivation function. And as it says, as specified in SP800-90A. Now, the job of SP800-90B is to specify the entropy extractors or the conditioning components. So what are those things doing in A? So if we go back to this idea here that this output goes on to SP800-90A and this conditioning component is optional, that's because you might be using this in the SP800-90A part of your design. So these are not great extractors. HashDF, hash, is not a great entropy extractor. There are proofs that they cannot be on their own a great entropy extractor, which we'll talk a little bit about. And the block cipher is okay, but it pretty much is a copy of what's here. So it's not a very useful thing to have there. So it's in the wrong part of the documents. The reason it's there is because SP800-9T, without an A, B, or C, used to be the sole document, and they put everything in it. And then they split it out into 3 documents, but left the derivation functions in A rather than moving them to B. Which I think was a mistake, but that's how they did it. So now we've got the conditioning components in 2 different documents where they should be in just one place. So don't be confused about that. But generally, I'd recommend using these message authentication code-based entropy extractors, because academically they've been shown to be good extractors, whereas the hash functions have been shown to not be good extractors. And the block cipher derivation function is a bit suspect too. All right, so let's look at these things. So the hash is an algorithm, and I won't go into the details of how a hash works because there's plenty of other places which will tell you how that works. But it basically takes some arbitrary size input and squishes it down into a fixed output size and works as a one-way function. So by looking at this output, you cannot work out what is in the input. There are various other things. You couldn't create you couldn't easily create two different messages which you knew gave the same fixed output, and that would be called a collision. And then and there are various other properties of hashes. You can read about that or watch videos on it. But if you were to put in a whole bunch of partially entropic data, it would squish it down and give you more entropy per bit. It wouldn't give you any more entropy, as we discussed in the earlier videos on the basics of entropy extractors, but it would give you higher entropy per bit. Then here we have the HMAC structure, and HMAC uses a hash function within it, and the same thing. It takes a message and it outputs a MAC of the message, but it takes a key. And the key is interesting because what it means is for any message you put in with one key, if you were to change the key, you'd get some different message. And so a MAC acts as a whole class of different smushes, right? You can smush it one way, you can smush it the other way based on the key. And that's what's called randomizing the hash, right? You've got a class of hashes where the key is defining what they are, and that's very good because you can show academically, and there are papers that show this, that these things are a good extractor, providing the key is independent of the message. So if you could control both inputs and pick them carefully, you could control the output. As in, you take the key and you look at the message coming in. You could choose your key so that some part of the output had a known value. You just keep running different keys until you got the answer you want. Something like that. So in that case, the key would not be independent of the message, but the key has to be independent, and that's easily achieved. So looking inside the hash, the HMAC, we start off with the keys. So you give it a key, and the key can be any size. And if the key is longer than the block size, which is the block size parameter within the algorithm, you would hash it to get some output. And if the output again was not the block size, you'd pad that with zeros. Typically, the size of the output of the hash will be identical to the block size, and so you just take your big key, hash it, and that would become K0, key 0. If the size of the key is equal to the block size, you just use it. And if it's smaller than the block size, you would pad it with zeros and use it like that. So this gives you an interesting insight into having keys that are too small. So let's say here I have my key, and it's all ones, say. And I have 50% of the size of the block size, so half these bits are key and they're ones and the rest are zeros. If I picked another key which was 1 bit longer and that extra bit was a 0, that would just tack another 0 on the end and it would be identical because you've padded zeros and now you're padding one less 0, but you've replaced it with a 0 in the key. So having a key of a different length doesn't necessarily mean you're going to get a different result from the MAC until your key is equal to a larger, or until your key is larger than the block size. So when you're using HMAC, use a key that's big enough, or you get these strange effects. So we've got our key, and then we do this, which is we take our key, we XOR it with a string of bytes of OX36, hex 36, XOR them together, and tack your input message onto it, hash all that, and you get this part of the next stage. You take again your key 0, XOR it with the output pad, which is a string of hex 5C values. That becomes the first part of this stage. And then you hash that all together again, and you take the output, and that is HMAC. So it's not particularly complicated. It is a bit computationally intensive because hashes are a bit computationally intensive, and you're doing 2 of them. That's and as we see a bit later, the CBC MAC is more computationally efficient. So now we'll look at CBC MAC. Now the inputs and outputs are the same. You've got a message, you've got a key, and it outputs a MAC. But inside CBC MAC, here is your message split up. And in the standard spec, when your message isn't an exact multiple of the block sizes, there's another thing you have to do. There's some padding you have to do, which is has to be done correctly. But in this case, since we're designing an entropy extractor or conditioning component, we can choose that the size of the input data is an exact multiple of the number of blocks. So when we're designing conditioning components, we just take as much data as we need and use the simple case. So we have an encryption block, which is AES, and because it's NIST, and then you have your key. Now we talked about why the key needs to be independent of the data. So what we've done in Intel chips is we picked a fixed key, and the fixed key was computed by taking the AES, the block cipher, and encrypting the value 0 with the key 1. And you get this random looking value, which is independent of whatever input the noise source might give you, because it isn't going to think up this big random value in hardware. So that's the idea. So the key is actually public. We don't need to keep that key a secret. It's not like keys usually are in cryptography. So we take all our messages. We start with what's called an initialization value of 0, XOR it with message 1, encrypt it, take the next message, XOR it with the output of the encryption, encrypt it, and so on until you get to the last block, encrypt it, and here's the MAC. And so every single bit that you've taken in is going to alter the MAC in a large way because it's being passed through the encryption block. And if you were to only have a single block, you would take some data, encrypt it with 0, XOR it with 0 so that you had the same thing, encrypt it, and this would be your answer. So a single block message authentication code is exactly the same as a block cipher, or the block cipher you're using. But as soon as you add a second or a third, then you now have a message authentication code. And so it's an important thing that your input data is larger than your output data when you use this as a conditioning component. Let's look at the last one, which is CMAC, or the last of the good ones. And they're good ones because they're MACs rather than just hash functions. And here we've got more or less the same thing, but the spec gives you 2 different ways of doing it. And key 1 is something that we compute. Key 2 is something we compute. And the difference is when we have an integral number of blocks of data, so like as with CBC MAC, we can optimize by making sure that the amount of data is an exact multiple of the block size. So all the data is filling these blocks. If you don't have that, this last block, which will be incomplete, you pad it like this and you use this K2, a different key. So of course we don't have to do this because we can choose to do this. We can choose to take in as much data so that it's an integral number of blocks. So you do exactly like CBC MAC until you get to the last block, and then you XOR in key 1, and you encrypt it, and you take the TLEN, the output length, most significant bits, typically all of them. So this is what we would do, is just this structure and not worry about K2. And there's a spec for choosing what K2 is, or taking your key that you've input and turning it into K1. Of course, if you're using a fixed key, you can pre-compute what K1 is and just hardwire that into your hardware or software. Okay, the last thing we're going to talk about is chaining extractors. Oh, it's not the last thing we'll talk about, but we'll wrap up after this. So you've got an entropy extractor, and the spec lets you have a chain of extractors. And so I might have the first extractor and the second and the third. And why might I do that? Well, this noise source might be more than one noise source, and you want to use a multiple input extractor that we've discussed in the previous video. Or you might have some statistical extractor. It's something that understands the properties of the data coming from the noise source and does some simple XORing or things like that to increase the entropy in a very simple and efficient way. But anyway, it lets you have chains. There is currently a discussion about how long can this chain be, and we might find that there are limitations on how long the extraction chain can be. The likely answer will be 3. And the same discussion is happening about DRBGs. How long a chain of those can you have? And the answer is going to be 3, I think. But that's not set in stone yet. But anyway, you can have one. But the most important requirement here is the last one in the chain. Whoops, come back. This last one here has to be a vetted conditioning component. These two can be anything you like, provided you can justify them. You have to, if you're not going to use a vetted conditioning component, you have to justify the algorithms you put here by putting some kind of mathematical argument together that shows why that is a good thing to do to the data to make it better, and how it will always make it better and not make it worse. If you could, all these 3 could be vetted conditioning components, but why, right? If you're using vetted conditioning components, just use one. That's sufficient. And we'll see a little more about why that it will be sufficient. So we'll look here, how much data do we put into our vetted conditioning component? So we've got our extractor here in the middle, and we're going to take noise source bits and put them in, and they've got some entropy rate. So the entropy rate is the entropy per bit, and X bits. So there's a total amount of entropy, and it's less than the number of bits. And it's contained within those bits, and we put it in. And what we get out is a smaller number of full entropy bits. So how big is Y? Well, Y is typically the size of your block cipher, or the output of your hash function, because that is what HMAC and CBCMAC and CMAC provide you with. So with the block cipher ones, 128-bit is the standard. With HMAC, you can go bigger. You can have 256-bit outputs, 512-bit outputs. But how much data do you need to put in? And the spec gives you some guidance on that. And here it is. It says, when using a conditioning component listed in 31511, that is the vetted conditioning components, the entropy of the output is estimated as this function, and the insides of this function is here. It doesn't matter what this is, but let's look at the inputs. So n in is the number of bits in, n out is the number of bits out, like I said, 128 or 256 or something, depending on what function you're using. NW is the internal width of the algorithm. So if that's AES, the answer is always 128. If it is SHA, it will vary based on which version of SHA you're using, SHA 256, SHA 384, SHA 512. Some of those will have different internal widths. And then entropy in. So this is, so let's say you had 1,000 bits in, but it was 50% entropy, you would have 500 bits. This would be 500 because 50% of 1,000 bits. So this function is purely a function of these things. Now you'll notice some things are not here, like the key. The size of the key is not relevant. So let's say you're doing a block cipher implementation, AES, with a 128-bit key or a 256-bit key. It makes no difference how big the key is. It just makes a difference how big the internal path is. And in AES, the internal path is always 128. So you may as well use the 128-bit key. It'll be more efficient, run faster, and not suffer from the problems of creating larger block ciphers. So when we run this, what we want to get is an answer for how much entropy is coming out. And what we actually want is full entropy. We'd like the extractor to be putting out perfectly uniform data. Now, it won't achieve that because it gets asymptotically close. And so what we have to do is pick how small a delta do we want from the value 1 bit per bit of entropy, 0.99999 something, and the draft SP800-90C gives us some guidance, but it's not standardized yet, and that is epsilon, the gap, needs to be less than 1 and 2 to the 32. And when we write some code and do that, we get these answers. If we put in 256 bits, this is for CBC MAC, so N out is 128, NW is 128. We're putting in 256 bits, or 32 bytes. We need at least 68.56% min entropy. The entropy rate is 0.6856 of the number of bits in. If we put in more data, now we can get by with a lower entropy rate because we're putting in more entropy overall. And we find out the answer is where epsilon is less than 1 and 2 to the 32, goes down to 0.45 something, and so on. You increase the amount of data you put in, the quality of that data necessary to achieve full entropy output is reducing. So if your entropy isn't good enough, by some metric, you can increase the amount you stuff into the extractor, and until you've exceeded, or your quality bound is going down as you put more in. And let's say I have 20% entropy, I would find I need to put in at least 896 bits, and I would probably put in 1024 to give me some margin. So here I can get away with 17.14%. Right. If we plot this graphically, here L is the length of the input in blocks. So L equals 2 means 2 times 128 bits, or 512 bits. Sorry, 256 bits. 3 is 3 times 128. So there's exactly these numbers, 256, 384, 512, and so on. So the different colored lines represent the different amounts of data that we're putting into the entropy extractor. And here is the entropy out. And you can see these curves all saturate at 128 because that's the size of the output. It can't go beyond 128. But if you were to zoom in on this, you would find that this is an asymptotic function, and even up here it never actually reaches 1. Now, if we follow the L equals 2 line, we see that on the bottom, here's the entropy rate we're putting in. So here's 20%, and it's not enough because we are now, almost 50-something% away from, or more than 50% away from full entropy. But we can come up here past the knee of the curve up to about here, and we say, oh, it's going to be somewhere around here. Now, if we go back, we see it's 68.56. So that's actually about here. So the blue line has got closer and closer and closer, and then when you got to here, the blue line is less than 1 and 2 to the power 32, away from the value 128. If you put in 3 blocks of data, then this curve saturates earlier, and you can see as you put in more data, the how much quality of data you put in goes down. But there's a somewhat diminishing returns going on here. These lines are getting closer and closer together as you put in more data. So you might find that it's much better off to have good data to start with, because then you can put less data in. So putting this together, there are some other details in the spec. So one of which was the input length must be fixed. Now there's an implementation guidance document 719, which is published as addendums against FIPS 140-2, or FIPS 140-3 these days. And FIPS 140-3 says if you're going to have a random number generator, it must be compliant to SP800-90. And it makes this change saying when we said it was fixed, we actually means it has to be a minimum size or greater. Because myself and everybody else in the industry complained that what's the point in fixing it? Nobody fixes it. They generally collect entropy into some kind of pool that they're extracting into until somebody asks for a random number, and then they start again. And so the amount of data you actually collect will be some minimum that you require, but you'll keep on pushing more in. And what we do in the Intel CPUs is we take a certain amount of data in that has been flagged by the health test as being healthy. Any data which comes with a bad flag that says this didn't pass the online health test, we will still put it into the conditioner, but we won't count it. So we have a 4-to-1 extraction ratio in the Intel chips, and you might get 5 blocks or 6 blocks, but those blocks will have been flagged as bad, or 2 of those blocks would be flagged as bad. At least 4 of the blocks are going to be good. And as soon as it's seen 4 good blocks, regardless of how many bad blocks it's seen, it stops conditioning and outputs the value. So the input length in Intel chips could be longer, usually isn't. The MAC key can be fixed. We've talked about that. But then when you go for certification, there's a thing you have to do, CAVP, Cryptographic Algorithm Validation Program. To build a system that is compliant to FIPS 140, you need to take all your algorithms and get those certified, which is a fairly simple process. NIST sends you some vectors, you run them through your algorithm, show them the results, and they will know what the correct answer should be, and if you've implemented it right, you'll get the correct answer. So this is just a little algorithm that you or process through which you test your algorithm, and then you can get a certificate. But when you implement CBC MAC, for instance, or HMAC, that's a general purpose algorithm, there's certification for it, but when they test, they don't give you a fixed key, the fixed key that you chose for your extractor, because you can. They'll give you any old key. So you still end up having to implement all the key scheduling hardware in AES, or the key handling logic in HMAC for different keys. If you were using just a fixed key, you just pre-compute that and wire it into the design. So while in 90B you can get away with a fixed key, when it comes to actually building a system and getting it through certification, you will find that would have been a mistake, and you actually have to cope with whatever key they send you for testing. I think this is a mistake. I've been petitioning NIST to change it so that you can say to NIST, this is the key we're using in our extractor, please give all my vectors in terms of that. But that hasn't happened yet. Derivation functions, we've talked about, they're in the wrong spec. They should be in 90B, and they shouldn't be keyless algorithms. They should be keyed algorithms like message authentication codes, because there are academic algorithms, so academic proofs, which give you the strong reasons for doing it that way. None of those conditioners are multiple input entropy extractors. So if you want to do if you want to use one of these, and there are good reasons for doing it, as we saw in the previous video, because multiple input extractors can be a lot more efficient. So you can't use this thing as a primary extractor, the last one in the chain, because none of the options in 90B are a multiple input extractor. I think this is a mistake. Again, we know the algorithms which are things like 2x and BIW, they make great entropy extractors, and they're very efficient. But we could use those earlier in the chain as our own proprietary algorithm, and we could point to the paper which proves them to be good extractors as our justification for using that. So you can use them in a chain, but you can't use them as the last one in the chain. You're stuck with the 3 options in 90B or the derivation functions. there isn't any guidance on what to do with a health failure. We saw in the initial diagram, they said you've got this health test, it outputs an error message, but what do? The actual tests they specify in 90B, and we'll look a bit later at online health tests, have a very high false positive rate compared to normal testing, as in given good data, they will output a failure quite often. In the case of the Intel silicon, we tune it to be about a 1% false positive error rate. So even though your entropy source is healthy, every now and then it will give a failure, and that is so that it has a low false negative error rate. There's a trade-off between these two values. We don't want a broken entropy source to push bad data through and it not get recognized by the test. So what we do is we take the history of the health tests, and if too many of them are failing, we say the entropy source has failed and raise an error and don't proceed to issue any more random numbers. But NIST doesn't say that. They don't say anything about what you do with the failure. And they do say things about if you go enter an error state, you need to report it. But they don't say an online health test is cause for entering an error state. So they've left this open, and you have to invent your own thing, and we invented our own thing. If your noise source is bad, as in low quality, it is producing not much entropy per bit, a low entropy rate, then just stuff in more data as per this plot. You're finding your entropys down here. Say, oh, I better follow the pink line so it saturates. So I'll go and use an extraction ratio of 8:1. At Intel, we use an extraction ratio of 4:1 because our entropy source is its quality is up here somewhere, so we're just fine. So that's it. That's conditioning components, or entropy extractors, in SP800-90B. It is an evolving spec. There have been multiple updates to it in the draft stages. It's been published as a spec for a couple of years now, but there will be another update to 90B coming down the line. So by the time you watch this, that spec may or may not exist. As of November 2021, an update to 90B doesn't exist, and there hasn't been any review period for that either, so it'll be a while. So thank you, and I'll see you in the next one, and we're going to move on to the topic of PRNGs, or DRBGs, the pseudo-random number generators. Thanks, and bye.